minus 2, minus 1, and this minus 1 half gives you minus 2. So that's another way. You can have more states. For example, between ML equals 1 and NS equals 2. You get a 0. You also have ML equals minus 1 and S plus 1 half, plus 1 half. Which also gives us
飛びでです、飛びで。国道6号飛びで前です。3時まで走ろう。
Some sort of trickery to evaluate this expectation value with a little less work than the traditional method, but still asks the question whether you can use degenerate or non-degenerate definitions. And that's an interesting question. In this example, it can help you visualize a little better what kind of degeneracies you have. We're continuing a chapter of history of physics. We're done with the reason. We're done with hybrid matter for the moment. So, WQV approximation.
Or
semi-classical approximation. So this is work due to 3 people, Wenzel, Kramers, and Riemann, in that incredible year, 1926, where so much of quantum mechanics was figured out. As it turns out, many of these discoveries, once the discoveries were made, people figured out that somebody did them before. And that person was the mathematician Jeffreys. 3 years earlier, 1923, the work had not become really popular. So some people like JWKB, but will not do that. No Jeffreys, but will follow this more standard notation. So these people were doing differential equations, slowly varying spatial coefficients. That is so approximation methods with approximation theory. We have analytic system of work on it. Now we can see things that are slowly varying in space. You might have a very simple Hamiltonian where nothing varies in space, constant potential. As soon as the potential starts varying slowly, we have approximation methods. Those are the methods we're considering now. We also consider, after we finish up time-dependent correlation theory, where things start slowly varying in time. So we'll have many things to do still. So this is called also the semi-classical approximation, because classical physics has tradition about the quantum wave function. So it is a lesson from which you want to learn something about the quantum wave function, learning them using classical physics. A quantity that is relevant here is the de Broglie wavelength of a particle. This is the Broglie. And many people say that semi-classical approximation has to do with the fact that quantum mechanical effects are not that important, and that may happen when the de Broglie wavelength is much smaller than the physically relevant sizes of your apparatus. So you have a particle like an electron, and if its de Broglie wavelength is very small compared to the aperture in a screen, the electron will go on like a classical particle. When the de Broglie wavelength is comparable to the size of the aperture in a screen, the diffraction effects of the electron will be quantum mechanical things. So the semi-classical approximation has to do with lambda being smaller than the length scale L of your physical problem. We will refine this. In fact, the whole search of understanding the semi-classical approximation is all about understanding this better, because it's a little subtle. We will end up deciding that what you need is that the Broglie wavelength, suitably generalized, varies very slowly. And we'll have to generalize the concept of the Broglie wavelength. We might get to it today. Mathematically, you can say, okay, I want this to be sufficiently small, so semi-classical limit is just the h going to 0. You should complain, of course, h is a constant of nature, it cannot be equal to 0. But on the other hand, you can imagine other universes maybe where h has different smaller and smaller values, which quantum mechanical effects offset much smaller scales. But at the end of the day, I don't want to consider h small as an ideal line as a classical approximation. And the implication is that for h small, you cannot say it's about h small. Example the Broglie. Taking a quantity with units, h has units, and saying it's small, it goes against lots of things. And things with units are not supposed to be small. This should compare with the situation we had before. We had a very nice and clean situation with derivation theory where we had a unit-free thing that we considered it to be small. This time we're going to try to consider h to be small, and it's going to be more delicate because it has to be more complicated as well. It's interesting, and that's why this approximation is harder in some ways to understand than the ones we've done in derivation. So how does this begin? It begins by thinking of a particle in a potential, E of x, and the particle has some energy E, and then if it's classical, as if we're imagining it now, it could be a three-dimensional potential. My sketch, of course, is just for one-dimensional. This is E, and you can solve for P squared, 2m E minus V. This is a notion of local momentum. Local momentum. Because it depends on x. Because the momentum the particle would have, when it is at some position x, it will have a momentum P of x. And now, nobody forbids you from declaring that you're going to define a position-dependent de Broglie wavelength, which is going to be h over P of x, is your definition, which is equal to 2 pi h bar over P of x. That's your local de Broglie. You see, the de Broglie wavelength, when we first started in 1804, was considered for a free particle. Always a state because you have a free particle with some momentum, it has a de Broglie wavelength. Why does the de Broglie wavelength work? Because when we write the wave function, it's in wave. With wavelength, we do the de Broglie wavelength. Wave function with the wavelength, we do the de Broglie wavelength, solves the Schrödinger equation. That's sort of how it all came about. It was all defined for a free particle, de Broglie defined it for a free particle with some momentum P. And it all made sense because you could write a wave function using that de Broglie momentum. It was in fact e to the IPX over h bar. That was your wave function. But here, we have a particle moving with varying momenta, and we don't know how to write the solution of the Schrödinger equation, but there's classically this concept, and we could define the local de Broglie wavelength, and we will have to discover what it means or how it shows up. And it probably shows up in some way. So there's two cases that probably we should consider, but before that, we look at the Schrödinger equation. The time-independent Schrödinger equation. So it's minus h squared over 2m, Laplacian of psi of x, is equal to e minus v of x, psi of x. All these vectors. That's why I'm using Laplacian, not second derivatives. But the right-hand side, well, if I put 2m to the other side, I get minus h squared, Laplacian of psi of x, is equal to 2m e minus vx. That's p squared of x, psi of x. That's the local momentum squared. Maybe it's a curiosity, but it's now nice that the left-hand side is the momentum operator squared, so it's p hat squared of the wave function is equal to p squared of x times the wave function. Kind of a nice result. Nice looking Schrödinger equation. I don't know if you've seen it like that before. It's an operator on the left, and on the right, almost like an eigenvalue. It's a real eigenvalue. If it were a real eigenvalue problem, it should be a number, not a function here. But it's a function that acts a little like an eigenvalue. It's a nice way of thinking of the Schrödinger equation in the semi-classical approximation. So, well, no approximation here so far in the semi-classical language in which you call this the local momentum, and thus define the certainly is an exact statement, no approximation whatsoever. Okay. Now, I want to know these two circumstances, of course. You have E greater than V, you're in an allowed region. And P squared is really 2m E minus V of x. And it's convenient to define h squared, k squared of x, a real number. You remember that P equal hk was good notation. We use the real number sometimes. We'll have here a local wave number as well. And if you're in the forbidden region, which energy is less than V, then minus P squared is positive, is 2m minus V. That is positive this time because V is greater than E. And that we also use to integration constant in kappa, functions that are exponential as well, h squared into kappa squared of x. And we could again add the wave number. It can be called as an imaginary wave number. And that's notation. So far so good. One more piece of notation as we work with this semi-classical approximation. We have not done any approximation yet. Solving the Schrödinger equation under those circumstances. H bar is an expansion parameter. Fine and correct, but a little something. So the thing that will help us in two times to understand the things is to write the wave function as a complex number. So suppose you have a wave function. We will write it as a complex number in the following form. Radius times phase. So the radius will be density, the probability density I claim is this, and there's a phase that I will write as e to the I over h bar s of x dot t. It's a little phase, because it's an imaginary number that's a real thing. S has units of h bar, or angular momentum. And indeed, psi squared is equal to rho of x of t, psi squared. The reason we focus on this wave function is that our solutions of WPB are going to have exactly that form, so we need to have an intuition as to what the observables of this wave function are. So the other observable is the current density, if you remember, is h bar over m, imaginary part, of psi star gradient psi. So this must be calculated. So what is this? Gradient of psi must be the gradient of this. Gradient is a derivative, so actually one answer the other. That's the first answer is a derivative. 1 over 2 squared of rho of x and t. That's the gradient of rho. Times the phase factor. Plus, now I have the gradient of this quantity, and this will bring down an I and h bar, the gradient of s, and then multiply by the whole wave function, because this factor remains and exponential remains. Now we can multiply by psi star to form what we need to get for the current. So psi star psi. So multiply by that, and multiply by the top line. For the first factor, I get 1/2 gradient of rho, the exponentials cancel. And for the second part, we get plus I over h bar, gradient of s, that's psi squared, which is rho. The imaginary part of this is equal to 1 over h bar rho, gradient of s. So finally, the current, which is h bar over m, and that's times that imaginary part, is rho, gradient of s over m. A very nice formula. Basically, it says that the phase factor function determines the current, and it also says that if you want to think of this, here are the surfaces of constant phase. Here's X phase, and this constant. So if you want to surfaces of constant phase, the current is a formula for that. So the current is proportional to the gradient. The gradient of the function is always proportional to the normal vector to the surfaces of two segments, discussed that it would be useful to find a position-dependent momentum for a particle that is moving in a potential. That was a completely classical notion, but helped our terminology in solving the Schrödinger equation, and set up the stage for some definitions. For example, a position-dependent de Broglie wavelength that would be given by, in terms of the position-dependent momentum, by the classic formula that de Broglie used for particles that move with constant momentum. Then, in this language, the Schrödinger equation took the form of the Schrödinger equation, the time-independent Schrödinger equation. Psi is equal to p squared of x. This is psi of x. I mentioned that it was kind of nice that the momentum operator ended up having sort of in the style of an eigenvalue, p of x. We then spoke about wave functions that the approximation would take the form of an exponential with a phase and a magnitude, so notation of complex numbers, so the psi of x and t would be written as rho of x and t, e to the I over h bar s of x and t. That's a typical form of a WKB wave function that we will see soon. And for such wave functions, it's kind of manifest that rho here is the charge density, because if you take the norm squared psi, that gives you exactly rho, phase cancels. On the other hand, the complication of the current was a little more interesting, and it gave you rho times gradient of s over m, the mass of the particle. So we identify the current as perpendicular to the surfaces of constant L, or constant phase, in the exponent of the WKB equation. Our last comments had to do with lambda, and we've said that we suspect that the semi-classical approximation is valid in some way when lambda is small compared to the physical length of the system, or when lambda changes slowly as a function of position, and those things we have not quite determined precisely how to go, and something we have to do today is understand more of the nature of the approximation. So the semi-classical approximation has something to do with lambda slowly varying, and with lambda small, in some sense, and seem to have an h bar in here that would make it small. H bar small, we also mentioned that considering the limit as a certain anti-value or vicious limit to which h bar goes to 0. So it's time to try to really do the approximation. Let's try to write something and approximate the solution. Now, we have a nice instructive form of the wave function there, but I will take a simpler form in which the function will be just a pure exponential. So, setting the approximation scheme. So, approximation scheme. So, that it just has a phase. You would say, of course, that's impossible, so we'll use time-independent Schrödinger equations, so s of x, and we will write psi of x from e to the I h bar s of x. So no, that's not true, right? Because the functions are more than just phases, are not just phases. We've seen the functions are more than the function of the phase density equal to 1, but that is important that the criticism is s now a complex number. So if s is a complex number, imagine I find that s is the norm of the wave function. So it's possible to do that. The function here as the exponential of the log of something. There's no loss of generality in something like that. Now we have the Schrödinger equation, and the Schrödinger equation is written as second x squared of x I over h bar x. Now when we differentiate an exponential, we differentiate it many times. We have a couple of things. We can differentiate the first time x and s prime down, and the second time we differentiate exponential, it goes down. So these two terms. The first one, imagine differential. The first one s goes down, and then acts on s I over h bar s double prime. That's just prime notation. And the other one is when you differentiate once here, it brings the factor down again there. So it's plus I over h bar s prime squared. And then the phases go there, and it can cancel between the left and the right, so this is equal to p squared of x. So I took the derivative and cancelled exponentials. So cleaning this up a little bit, we'll have this term over here that the h's cancel, the sign cancels, and you get s prime of x squared minus I h bar